Hey guys, we're going to look at Rutherford's model and the limitations that it was faced with, and we're also going to look at Bohr's model. Okay, this is the beginning of chapter 5, and we're going to eventually work into something called electron configurations. Now, there's 5 basic models of the atom. Just to review, let's look. There was Dalton's model, had no internal structure. It was indivisible, indestructible, and it was a tiny solid sphere. Okay, then we had J.J. Thomson's model. After he discovered the electron, he determined that the electrons are spread out like plum pudding. Okay, and it was a sphere of positive charge that the electrons were basically spread around in. Okay, so you have your positive sphere and your negative raisins or your plums. Okay, then Rutherford actually got credit to discover that there's a dense central portion of the atom called the nucleus. Okay, and electrons were still scattered around it. Now, remember from the gold foil experiment that he proved the nucleus was in the middle, that the alpha particles were deflected off the nucleus, and there was some kind of angle and deflection based on the 2 positive charges, the one of the alpha particle coming in contact or coming close to the nucleus and bending off and shooting. And then he determined that the central portion of the atom is the nucleus. Okay, now there's some limitations with Rutherford's model. Okay, he could not explain the chemical properties of the elements, and he was unable to explain why metals or metal elements or metal salts produce light when heated. Okay, so he didn't understand that. They had no concept on that at this point in time. So, for example, what I'm talking about is if you take a piece of iron, you get it red hot. Where is that red hot color coming from? And then you can get it even hotter, which is white hot. That's basically right before iron turns into a liquid. Okay, now we're going to look at the next model. It's called the Bohr's model. Okay, it was the Danish scientist Niels Bohr, and he did a little extra studying on the previous models of the atom. Okay, he was a student of Rutherford, and he incorporated in his model newer discoveries about how energy of an atom changes when an atom absorbs or emits light. Okay, so when you shine a light on an object, what happens to the waves of light that hit the atoms of the metals? Well, something is going on. Something happens. Okay, and this was all figured out or discovered around 1913. And he based his model solely on just the hydrogen atom, and it only worked for the hydrogen atom. Okay, Bohr's finding regarding electrons, pretty interesting. Okay, he found that they're in fixed paths or orbits. Okay, kind of how like the planets rotate around the sun. Very similar. Electrons rotate around the nucleus. So we have the nucleus in the center, and then we have these different rings. Okay, these rings are basically where the electrons sit. Now they're different distances. Okay, they're not all the same. Big jump here, small jump here. And they're represented by a little n. N being the first one in, and as you go up, the number increases, and so does the potential energy increase as you go from n equals 1 to n equals 5. You're getting further away. Okay, so it's like a book on the floor versus a book on a very high shelf. There's more energy. Okay, he also proposed that each orbit has fixed energy, just like different shelves in your room. The higher you go, the more energy it has. Okay, so an energy level is the fixed energies an electron can have. Okay, your book also uses building floors. Okay, now there's something called the quantum. Very important definition, kind of a weird spot for it, but it's a term that we're going to need to know. A quantum is a unit, okay, is the amount of energy required to move an electron from one energy level to another energy level. Like climbing up from the first floor to the second floor, it takes energy to move up. An electron cannot move up from one energy level to another one without getting a minimum amount of energy, which is called the quantum. To go from the first floor to the second floor, you need a quantum of energy, a unit of energy. Okay, so let's look at this little ladder here. This ladder, okay, notice it's on the grass and it's up on the wall, but the rungs are all different distances. So it's close to the grass. This is called ground state. And then towards the top, we're going to learn something called excited state. And they're all different distances. Now, at higher levels, it requires less energy to move or jump from one energy level to another because they are closer together. So it requires more energy to go from here to here, then here to here, then here to here, then here to here. They're all mapped out. You can actually find the energies related to each one of these jumps. Okay, that's something he studied. Now, electrons have lower potential energy towards the nucleus, just like a book on the floor. It's not falling as far. Okay, so potential energy of an electron depends on the size of the orbit and is lower for smaller orbits. Okay, so energy is proportional to distance. Okay, so as you go up the ladder, you're going into an excited state because energy is being absorbed. Potential energy is going up. So, in conclusion, Bohr's model only provided results in agreement with experiments using the hydrogen atom. Bohr's model failed to explain the energies absorbed or emitted by atoms with more than one electron. So at this point in time, he was only able to work with the hydrogen atom. Okay? So his model gave results in agreement with the experiment for the hydrogen atom, as I said, and still failed in many ways to explain the energies absorbed and emitted by atoms with more than one electron. Now, why is this? It's just a phenomenon that he noticed. Okay? And we're going to stop right there. Okay, so this is the end of part 1, and we're going to continue the second half of 5.1 next time.